Welcome everyone to our first press conference at the EGU2018 General Assembly. There are 8 press conferences that we are organizing for you this week, but there are also a number of scientific presentations that you are more than welcome to go to. In fact, there are 17,500 of them, and we are expecting over 14,000 participants this year. I am Barbara Ferreira, I'm the EGU Media and Communications Manager. I think all of those in the room know me, but for those watching remotely, I should introduce myself. So I'm helping here at the Press Center this week together with 3 press assistants, and you are welcome to email us or come and speak to us if you want to book interview rooms or have access to documents relating to the press conferences. And our media portal is media.egu.eu, so you can check it for press releases and other handouts that we'll be giving out this week. Our first press conference is called Eavesdropping on the Ocean and Cities, and we have 2 speakers today. The first one is Jordi Diaz, and he's a researcher at the Institute of Earth Sciences of Almera, of the Spanish...
Yeah, it's Catalan, in fact,
okay,
it's even worse.
the Spanish Scientific Research Council in Barcelona, in Spain. And then we'll have Pierre Cauchy, who is a PhD student at the Center for Ocean and Atmospheric Sciences at the University of East Anglia, United Kingdom. And I will, as with the other press conferences this week, both our speakers will give their talks, and then we'll open the floor for questions from the journalists here in the room or those watching remotely. And I'll now hand over to Jordi. Thank you.
Okay, thank you, Barbara. Hello, what we'll talk here is about seismic noise recorded within a city, inside a city. So the object of our investigation is just that. We put a seismometer, seismic recorder, at a building inside Barcelona, and we identified a number of signatures, a number of signals, and we want to know what's the origin of those signals. And as you can see, some of them are quite amusing, at least for us to see. And we can refer to, there are a large different of activities, but the most remarkable are, first of all, the traffic. We can monitor the traffic in the roads beside the building. We can also survey the subway trains, the subway system in Barcelona. And then we have we are close to the Football Club Barcelona Stadium, so in fact we can get information every time there is a goal. Every time there is a goal from the Barca, not from the other ones, because people jumps, and then the shaking is recorded at the institute. Also, sometimes we have beautiful recordings on rock concerts, particularly Bruce Springsteen or U2, which has been carried also in this stadium, and again make the earth vibrate. And then there is a large number of other activities, from marathons, runners, firework festivals, civil works, also natural features, as for example, every time there are storms, or in fact the oceanic wave, which are also recorded even inside the city. What's the utility of all this? Well, in the beginning of my survey, that our motivation for installing this station was mainly for outreach and dissemination, especially when there are people, students visiting our institution, just to show them how a seismometer works. But then we realized that having a look on all these kind of signals may be of interest for a certain number of points. We can say that we think that it may have a potential for surveying of, for example, the traffic. Of course, there are other systems which are widely used here and there, but seismics don't need to be close or beside the road. It can be some meters behind and some hundreds of meters behind, so it can have some potential utility. We can also use them to monitor the response of different buildings and structures to different kind of shading, and then there are some questions more related to research itself, which has arisen, in particular some particular points about which is the origin of long periods signals from trains, from subway, questions related to acoustic and mechanical couplings, and others. Okay, just to show you some examples here. For example, is a record. This is a record of the seismic vibration, Each line corresponds to 1 hour, and this is 4 days. And let's say that the wider, the blackest it's the signal, more energy represents. So we can easily identify the nights. This is the night period, this is the other night, this is the previous night, where the lines are thinner, so the noise related to traffic is much lower. And then here in the top, this is Sunday. You see there is a large difference between Sunday and working business days. And also it's nice to see, you see in the business days, this kind of banding about blacks and whites. That's in fact the traffic light regulated circulation in the diagonal avenue. If we move to the subway system, well, the subway system in Barcelona stops at midnight during Monday to Thursday, and then in Fridays extends 2 hours, and in the night from Saturday and to Monday remains open all the night. So in fact, if you look at, let's say, around midnight, in a special band of frequency, which is interesting, in fact, because there are very low frequencies, periods between 20 and 120 seconds, we can see that this is, Tuesday, Wednesday, Thursday. There are no energy here. The energy starts at 5 o'clock in the morning, but the nights of a Friday and the night of a Saturday, you can see every week how the thing works. In fact, if they make some kind of strokes, which is not unusual in Spain, you can follow also the evolution of the strokes just looking to the seismic data. You can see, for example, this day is the 12th of October is a public holiday in Spain, and so is the night before, which is also working. Okay, if we go to what we call the foot quakes, or messy quakes, or whatever you want to call them, to fact out the recordings of people shaking during goal celebrations in the football stadium. In fact, this is the seismic record during a match. This is actually last month's Barcelona-Chelsea match in the Champions League. Also, you can see the amplitude is a measure of the shaking. So this is, you see in the beginning, here, this is quite large and then becomes thinner, and then again it's large. Also, you can see this in the spectrogram. That's people arriving to the stadium, looking to the match, and then taking back home. And in particular, the goals are seen here. This is the first one, second one, and you can see that the frequency contents cross all the band between 1 and 10 hertz. This is fun about the same, but last year, maybe some of you will remember, that was a comeback from the Barcelona versus Paris Saint-Germain. They have to win 6-0, 6-1 or something like this. They do the last goal in the very last minute, so this was really the bigger celebration related to this. Okay, this is not surprising, but is attracting to the people. Another kind of events, so this is not very, well, the figure is not complete here, but anyway, in 16, there was a Bruce Springsteen concert also in the Barcelona Stadium. We are at about 500 meters from there, and we can record the seismic, maybe you see here better, yeah. This is the encore part, the very end of it was nearly 4 hours of concert, but this is the last part of the concert. And it's quite nice because especially we can do the spectrogram, so this is time, this is frequency, and the colors are for energy. You can see that every single song has a particular pattern, and you can identify from the seismic data when we are moving from one song to the other. Also note that there in the goal celebrations, that is people jumping, you can see that how the energy is distributed all over the 1 to 10 hertz band, while here you see what we call harmonic structures. You have energy localized in precise amplitudes. This is because people is not really jumping, but are really dancing, moving in a coordinate way, all around. And as I said, we have also a number of other issues that can be detected. Here, for example, this is the Marathon of Barcelona crosses close to our stadium. And in fact, we can detect the runners. These are the signal of the runners moving around. And if you look to the frequency, this is close to 2.8 hertz, which equivals to 170, how you say that? I mean, steps per minute, which is the usual ratio. You can see also the record of fireworks. This is the signal. This is the wind increase. This is meteorological data that you can see also in the seismics. Those are matches in the basketball arena, which are also pretty well recorded, and it's not easy to understand. And we have, in fact, a number of different things that, if you want, we can go to further detail, but I think we are on time to stop here. So we'll be glad to answer all your questions, sure. Thank you. Okay.
Okay, so that's me. Hello, can you hear me? Yep. Okay. So I'm Pierre Cauchy. I work at the University of East Anglia in Norwich, and I'm working in combining passive acoustics monitoring. I'm combining passive acoustics monitoring sensors to autonomous submarines, and the aim of this research is to develop new ways of observing the ocean. So I'll give you a few examples. I can monitor the marine life. I can detect and quantify physical processes and weather events. So I'll show you a few examples of that. And also I can detect man-made sounds. So try and measure the anthropogenic noise and the contribution of human activities into the oceanic soundscape. So first, this is the submarines I'm working with. We call them gliders. They are autonomous. They can cruise in the ocean for a few months and thousands of kilometers. They dive as deep as 1,000 meters, and they carry any sensors we want them to carry. So I can just put hydrophones on them. The most useful feature for me is that they are buoyancy driven, which means they don't have any propulsion system, and that makes them very quiet. I think if you want more details, there are glider sessions in this conference. So yes, they allow us to monitor the ocean with reduced ship and man presence. They are not restricted to good weathers, and they are very quiet, which is good for me. So here is how we sample the Mediterranean. That's just 5 deployments I've made. So for each of them, it just takes 1 day to put the glider in the water. It goes for a few months and comes back, and we recover it, and we have the data on it, and we can cover this whole. So that's the northwestern Mediterranean between France, Spain, and Sardinia and Corsica. Sorry. And we can monitor on various depths from the surface to the bottom. We have a large spatial coverage, and we can monitor all year long. So at the bottom, this is one example. It's a few weeks of recordings. That's a spectrogram. So we have on the y-axis the frequencies. The time is on the x-axis, and the energy is shown as it's color-coded. So when it's bright and yellow, it's full of energy in that frequency. And if you zoom, if you know what you're looking for, and if you look at the right scale and the right frequencies, then you can detect some events. So this is, for example, how the wind noise is, how we detect and measure the wind. If you look at those frequencies between 2 kilohertz, 2 to 10 kilohertz, then you can just look when you have energy, you have high wind speed events, and that's something I'm working on now. And also, if you look at other frequencies, lower frequencies, we can see those patterns every night. We have nights are noisier than the days, and this is related to fishes singing during the night. So that's something to investigate. So first is the wind speed measurements. It's a paper that is currently under review. So as I said, just looking at the right frequency band here, you can create a time series of high energy and high wind speed at the surface. And that will allow physical oceanographers to have a nice measurement on the air-sea interactions and how the wind is exciting the sea surface, and that allows to measure the exchanges of energy and temperature between the two, the ocean and the atmosphere. And that's used for calibration of the satellite measurements and then improvement of the climate models. Because the glider allows us to go and measure somewhere you can't go with a boat or you can have a buoy. As an example, we can send gliders into hurricanes. It's been done already, not with the PAM sensors, but I know we can send a glider there. So one of our future experiments could be having one deployed in a hurricane area and measure those very extreme events. These are the fishes. So just it's easy to hear them singing at night. They are loud, even though they might be hidden somewhere. They are only active at night, so it's kind of complicated to find them and count them in another way. And it's not done yet, but there was this paper here is a brand new paper, and they shown that some fishes in this area could be used as an indicator of the health of their Posidonia grasses. So to know if the reef or the shore is in good health, you can just look at the fishes, and if they are here, they're noisy, and then you can know whether how the health of the ecosystem is. And again, with the gliders, you could just cruise along the shore and see the areas of good and bad health of your grass. This is the funniest one. I have sounds here. So that's how we detect the whales. Again, whales are mostly underwater animals, so it's good to be able to hear them, and that allows us to monitor them during night, during storms, when it's hard to detect them from the surface. So here are a few sounds I can play. These are... Does it work? No. Oh. It worked earlier. I'm sorry. So those are long-finned pilot whales. Maybe it's my fault. I'll try the other one. No. Okay, so it worked before. So on this top panel is long-finned pilot whales. I've recorded them during a cruise near the Faroe Islands, and that's a huge pod of pilot whales. There are about hundreds of them singing. Well, it's way better when the sound works. Maybe I can try something. Oh, sorry. Does it work? Okay. So you can hear whistles and clicks and all those sounds that whales use to hunt, find prey to eat, and also those whistles are meant to keep the social cohesion of the group. So it's both communication and hunting sounds. And if it stops, yeah, okay. Then I have this other recording of sperm whale and dolphins, so it's a different kind of sound. This very regular, every 2 seconds click is from a sperm whale, and that's an easy to identify and recognize sound, and this can allow us to detect the presence of a sperm whale. But also, if you zoom on the click and the structure of the sound, then here you can you can find the size of the whale just by listening to just by having a close look at the sound. I can know that this is a 12 meters long sperm whale. So using the system, you can map the presence and the sizes, density of the whales in the Mediterranean. Now for the anthropogenic sounds, I have two examples here. The first one is a seismic survey, so you can hear the air guns towed by it's towed by a ship, and you want to be noisy enough to reflect on and under the ground to know the structure of the sediments. So this is what it sounds like underwater. I have only the first 30 seconds. So it's even too loud for my hydrophone, so it's all clipped. The sound is not very good, but you can hear a few whistles from a whale, and every 10 seconds this clapping is the air gun. And that's kind of sound you can hear from very far from the survey. And so that could be used to survey the industrial activities of survey ship, and to assess the contribution of those activities to the marine soundscape, and see how it interacts with marine life, and maybe protect marine protected areas, or see how the regulations work, or the mitigation techniques. And the last one down there, I don't have the sounds, but it's it's 4 days of deployment, and you can see all those low frequency, full of energy moments are ships passing close to the sensor, to the glider. And this bit here, I won't zoom in, but it's an acoustic trial from a military ship. So they are doing hydroacoustical tests to see how the sound propagates between fronts and in interesting areas. And that's it. So just to summarize, we are using very silent robots and acoustic recorders that allows to monitor on a very long term and low commitment from people and ship. It's absolutely non-invasive. We are not making sounds, just listening, and it allows to monitor the marine life, the ecosystem's health, helps for climate models improvements. So we're hoping to use those for storms monitoring, and also to measure the noise pollution. Thank you.
Thank you very much. That was fascinating from both of you. We'll now open the floor for questions from those here in the room or those watching remotely. Are there any questions here? Or does everyone rather approach our panelists after? Okay.
It's always worth asking a question, isn't it? Jonathan Amos, BBC. Jordi, I'll start with you first of all. Can you say something about the position of your equipment, where it is exactly, what it is?
The equipment is a seismometer. It's located in the basement of our institute. In fact, we have a couple of them. The first one is an educational seismometer developed by British Geological Survey, in fact, and then which was there just to show people how these instruments work. And when we realized that we have interesting signals, in fact, we deploy a, let's say, professional use one in the basement. So it's broadband seismometers, and then Matrix 1 can give you further details, but in fact it's able to record frequencies from, let's say, 100 periods, 100 seconds, or even more, to 100 hertz, something like this.
And your distance to the nuclear is what?
Distances, we are about 500 meters from the Barcelona Stadium, and we are about 150 or something like this from the Diagonal Avenue, which means the source of traffic and also the place where the subway lines are running. So we are in this order of hundreds to some hundreds of meters. It depends a lot of what are you willing to record, but in fact, we can see that at these distances of some hundreds, we are able to detect a lot of different things.
For engineering purposes, some people look for the changes in the resonant frequency of structures, don't they, to test whether, I don't know, rock structures are changing, whether they've got cracks and all the rest of it. Are you looking to do any of that work around Barcelona?
In fact, we are not engineering, but we have now trying to contact people in the engineering faculties in Barcelona. When they do this kind, of course, they do this kind of surveys using accelerometers, in fact, but they usually put the instrument inside the building to be done. So, in fact, the interesting thing is to see here, we are at about 500 meters, as I say, from the stadium, if we center in this particular case, and we are seeing the same thing, so it will be interesting to at some point to compare data acquired inside the building and outside and see if the information is the same or not. Also, we think that it's quite interesting to note that the kind of shaking during the matches celebration and during the concerts is very different, and we wonder if this can be of interest to progress in the knowledge of this part of engineering. But it's something that we have to contact with these guys because we are most used to deal with Earth interior that we build it.
Good. And then a couple of questions for Pierre. The frequency at which the fish are singing is what? I think the wind was at 2 to 10 hertz, wasn't it?
No, it's 2 to 10 kilohertz for the winds.
Kilohertz
It's
for the winds.
Yes,
right.
And the fishes are a bit lower frequency. I think the peak is around 700 hertz. So it's, you can detect them from 300 to 1 kilohertz.
Right. And the differences in wind speed, that's just a change in frequency, is it? Yeah.
No, it's just a same frequency, just a change of sound level.
Okay.
So the faster the wind, the louder the sound.
Right.
But the wind speed it makes noise at every frequency. You
Yeah.
just zoom on those ones because they are where you have the least other contributions. So you have only the wind at this frequency.
Right, I got you. And the glider just a battery operated bladder. Is it that makes it come up and down and up and down?
Yes, that's it.
Yeah.
And then it has wings, so it can go where it wants to go and come back.
Yeah, good, excellent.
Hi, I'm Olive Heffernan. I'm a freelance science writer. I just have a couple of questions for Pierre. The first question is, I'm interested in knowing whether these ocean gliders could be used to inform us a bit more about the high seas, because obviously that covers 50% of the planet, and yet 5% of it is explored. So I just wonder, can they be used, in areas kind of beyond EEZs? And how informative do you think they'd be? And also, I'm interested if you could you say a little bit more about their ability to sort of inform on harmful ocean noise, in terms of feeding into environmental impact assessments for, say, seismic surveys in the ocean?
Okay, so about your first question, I think we can now cross the Atlantic with a glider. So yes, they can. They are deployed in Antarctica under the ice. So you can take them using a ship wherever you want, and then they stay for a few months. So you can send them virtually everywhere. And about warning when they detect something, we have now integrated sensors, so you can have some onboard processing. And if you knew what you were looking for, then you can detect it and send the information as soon as it's detected. So it's near real-time detection and warning. Yes.
Are there any additional questions?
Hi, this is Holger Kroke for planetera.de. Question for Pierre. Are your sensors able to be put as an additional payload on existing gliders, or do you have to use dedicated gliders for the hydrophones?
Yeah, I use 2 different sensors. The first ones I was using are autonomous recorders. So they were designed to be attached on wheels. So you just tape them around the glider, and it's an additional sensor. It has its own batteries. So most of my deployments have been made with those sensors. I just know someone deploying a glider, attach my sensor on it, and it doesn't affect the mission. And now we use also integrated acoustic sensors, so they're a bit better. They can have this onboard processing, but they need to be in a dedicated glider mission. So we have both.
Thank you. Are there any additional questions? If not, we'll finish here, and you are welcome to approach our panelists and book one of the interview rooms we have on the side. And our next press conference is at 11:30, and it's on ESA's latest swarm satellite data. I hope to see you there. Bye. Thank you. Thank you very much.
Welcome. Thank you.